Hi, and what we're going to do in this particular video is look at recursion over lists. Recursion is a very powerful feature with lists. So what we're going to do is just work through some examples. You're welcome to read the lecture notes. Now, in an earlier video, we had a factorial function, a custom factorial function, which we defined in the following way. Input parameter n, condition 1, and remember these are different notations. List notations slightly different. If n equals 0, we will simply result and return 1. Otherwise, as long as n is greater than or equal to 0, what we return is n times recursively calling the factorial function n minus 1. Now, because this is our own inbuilt function, there is no prelude function called factorial that we are overriding in this particular instance. There is no ambiguity for us just to simply say, what's the factorial of 3? 6, because that's the same as 3 times 2 times 1. 4 times 6 is 24. 4 times 3 times 2 times 5 times 24, 120. 5 times 4 times 3 times 2 times 1, and so on. And it actually works it out recursively by calling the function with 1 removed from the number and then recalculating this multiplication and so on until it resolves the question. So this is a very simple example of a recursive. This is called the base case, the case at which essentially you have n equal to 0, which in the case of lists will be empty. And we'll come to it, and this is the condition in which to call the recursive function, and the result, you notice, is simply a call to and some operation on a call to the factorial function. So let's have a look at the prelude function of summing. So with prelude, you have a sum function for lists. Give it and if I type this correctly and not put the brackets in the wrong place, if I give it that, it simply sums all of that. What's the logic of it? Well, the logic of it is, and here I'll just create an override for us. Okay, so what are the types that we're dealing with? Easier if you see this. This is an override. We're passing it an array of integers, and the result is an integer. What actually does it do? Well, the first condition is if you're trying to sum an empty, you simply get, that's the base condition. If you sum the list, and remember it's always head and tail is the way we define it, the result is the x plus the tail recursively called into a sum. Now there's going to be an ambiguity here because there is a prelude sum. This creates an override, so I need to make sure I call my own, which is in the main, and the main is because I'm in the main file, and over here it's complaining because I want to call my own. When I call my own, it'll essentially operate in exactly the same way. There we can create our own double every item in a list. So have a look at this one here. The two data types are, again, integer list square bracket and integer list result. And what's the actual conditions? Well, the base case, if you're dealing with an empty list, is simply return or give you the result of an empty. Otherwise, using the notation with x and tail, you will take x, well, you multiply 2 times x, and it'll be prefixed on the remainder of, let's make some space so you can see what I'm saying. And again, we have the ambiguity issue. Again, bear with me a second. Right here, double all, well actually we don't in this case because there's no prelude double all, so it's not going to complain. That's the first item, the head. That's the notation which tells us we're dealing with a list, and so the remainder is doubled. We come back around here and it picks out each item and doubles it. So let's evaluate it over here. Let's give it a list, 1, 2, and over here it gives us 2, 4. If we do 1, 2, 5, it doubles each item. So that's a very, very simple, and again we're calling it recursively under a particular condition, not this base condition, but under this particular condition here. So let's have a look at another one. Let's have a look at another. Let's have a reverse. Reverse is also a prelude function, and we're going to just create an override here to look at the various conditions. So if we're trying to reverse an empty list, we just get back the empty list. If we are calling reverse, and there's our standard list notation with the X as the head followed by all the remaining items, then we simply call reverse on the remainder, and we use this notation to flip it around the other way. Again, we've got an ambiguity, and you'll see the ambiguity. There's a prelude, and yet you've created an override. So I'm going to call my own to resolve that, and then over here let's test it out. So I'm going to call my own main.reverse. I could call the prelude version. Let's pop in a blank. It gives back a blank. Let's put in 2, 3. It gives back 3, 2. Let's, as we know, a word is itself understood as a list of characters, so it can reverse that as well. And notice, because I haven't here in my override specified the types, as I do in some previous examples, it creates a polymorphic quality. So I could do this, and it reverses it. Good. So you get two things out of this, I would hope. The first is to notice that you can create your own custom functions, always having a base with a list, and then you recursively call. And the recursive relies on this notation in all these cases. You don't specify types, then the list's types can vary enormously. So I could do, for example, 3.4, 4.5, and 6.7, and it will reverse each item because I haven't specified. So it's a polymorphic function. The type, not type independent, but it allows multiple types in here. Sum and reverse are both prelude functions, and so by creating this override here and this one here and calling it recursively, I had to say I'm calling my own version. So that's a way of referencing back to the one that's in here rather than prelude. If I'd replaced that with prelude, I'm not quite sure what the behavior is, it would go probably a little. It did something there. Let's remove that, and let's just see what happens if I don't call mine but I call the prelude on it, and it still works because prelude reverse follows the same logic. So by making these patterns visible to you, although they're overrides, you can see how they work. Let's have a look at one last one. There's a prelude function called zip, essentially, which the logic is, and this notation allows me to specify the head. So it creates a list, which is a list of a tuple lifting the head or the corresponding head from each item. So let's define that in a little bit more detail. First of all, I need the base case. So if I'm going to operate on an empty list, okay, actually technically what we really want to do is, okay, let's just get the logic of it right. We have three variations for the base case. We have a list, and then we have an empty, gives you an empty. We have an empty list. Second list which is populated, gives you another empty. A third one is we have two empty lists giving you an empty list, and the fourth condition is where we have a populated first list, a populated second list, and the condition is for the recursive action is to lift X and Y, the head items, as a tuple, and then recursively call zip on the remaining statements within it. And again, we have the ambiguity because zip is also a function in Prelude. So this is slightly more complicated. We're giving it a list, second list, and it creates a single list made of tuples lifting the first item. These combinations are the various combinations of the base case, which you can actually, interestingly enough, replace all of them with two wildcards. Now let's have a look at the logic of that. The logic of it, not entirely happy. The pattern match is saying it's redundant. Okay, the logic of this particular type is that strictly that condition should appear first, and if immediately afterwards you add wildcard 1, wildcard 2 to cover every other case, you would in theory get this. Let's remove those and that, and let's have a look at the issue here for this particular case. Different number of arguments, yes, so that's not the right way around to write it, but the point here is that syntactically this environment's just struggling with it. But these three can be replaced by a single pattern match to give you an empty. For the time being, I'm not going to do it because syntactically this seems to create a problem for the environment. So we're interested in the fact that all of these cases are recursively calling the function we've defined in order to evaluate the statement. So it's a recursive evaluation